Can still see it okay?
Yes.
Yeah.
Okay, so when you're reading a sentence, it's kind of expected that you recognize when you're being fed ordered pairs. So like if I'm just reading this sentence here and I say, hey, at a temperature of 5 degrees Celsius, the corresponding temperature in Fahrenheit is 41 degrees. If the temperature is 10 degrees Celsius, the corresponding temperature in Fahrenheit is 50 degrees. It's kind of expected that coming out of a pre-calc class, you just recognize that you've just been fed 2 ordered pairs, 5 degrees Celsius. And ordered pairs, when you're working with modeling problems, they're not just numbers. Even though we usually don't write the numbers, we need to understand that the numbers have units. So it's not 5 and 41 like you would get if you had a y equals mx plus b kind of thing. It's 5 degrees Celsius generates or corresponds to a temperature of 41 degrees. And I really could write this particular relationship is what we would call invertible. It's an inverse relationship. I could actually write the ordered pair in either direction, but I'm going to write it in the order it was written in the paragraph, just for conversation purposes. So I'm also told that if I have a 10 degrees Celsius temperature, that is corresponding to a Fahrenheit temperature of 50 degrees Fahrenheit. So the first thing is I need to be able to read a sentence and understand when I'm seeing an ordered pair. And what you have to understand also is that there's no way in hell I could show you every possible way information could show up as ordered pairs in a paragraph, because there's infinitely many ways that could happen. So the general expectation is that you read with care and think about what you're reading. Is what I'm reading ordered pairs? Is it a rate of change? What information is being provided to me? So the minute that I understand that I have 2 ordered pairs, I know that I could plot them in a Cartesian coordinate system, right? So, and I don't need to put numbers on the axes. I can say, hey, maybe this is over 5 and up 41, and then it would be over 10 and up 50. So it has to be up a little bit higher. And I've got now I have a couple ordered pairs. Input 5, output 41, input 10, output 50. And I know that there's a line that goes through those points. And it's supposed to be straight. So once you know that you have 2 points, even if you don't draw the picture, you know that 2 points establish a line, and that if you have a line, you can calculate the slope of the line. But if it's an application problem, the slope isn't change in y over change in x, because there is no y in x. In fact, the vertical axis is a Fahrenheit axis, because I put Fahrenheit in the output position. And the horizontal axis isn't an x-axis. What is it? It's a Celsius axis, because I plotted Celsius as the input variable. Does that make sense?
Yes.
There is no x and y. This isn't a generic problem. This is a modeling problem. So last week, the homeworks all said introduction to linear functions. Well, now we're doing linear functions, but in a particular context. So when you look at the titles of this week's homework, it says linear modeling. And modeling is just that. It's modeling the real world using mathematical functions. In this case, a very simple function. So it isn't going to be delta y over delta x. What is it going to be? It's going to be delta Fahrenheit over delta Celsius, right? You do rise over run, and the rise is going to be a change in Celsius. Sorry, the run is going to be a change in Celsius, and the rise is going to be a change in Fahrenheit. So when you calculate the slope of this line, it isn't y2 minus y1 over x2 minus x1. It's literally 50 degrees Fahrenheit minus 41 degrees Fahrenheit. We don't usually write the units on, but in the homework that I make you do, I ask you to include units on things. Why do I ask you to include units? To try to keep you mindful of the fact that the number, even if you don't put the units on it, the number has units. And you need to know what the units are to interpret things. You can't make interpretations if you don't know what the units on the numbers are. So the delta Celsius that corresponds would be, because I put the 50 first, I have to put the 10 first that corresponds to the 50, right? Have to be consistent. Doesn't matter which ordered pair I put first, but I do have to be consistent here. If I put 50 first, then I have to put 10 first. If I put 41 second, I have to put the 5 second. And then you do this subtraction, so you get this number, 9/5. But what are the units on it? Degrees Fahrenheit, degrees Celsius. So even though we usually write the number without the units, guess what's there even if you don't write them? Guess what's there even if you don't write them?
The unit.
The units are there. Whether you write the damn things or don't write the damn things, they're there. Which means that number has an interpretation. What is it? So one of the things in the homework you're asked to do is interpret the slopes of the lines. But to interpret them, you need to know what the units are on them. So this is the big idea, is that the numerator always has to be the what? The outputs. So whatever the output units are, that's the numerator units. And the denominator is the change in the inputs. So the denominator is always going to be whatever is on this horizontal axis. It's going to be the input units. And so this has an interpretation. I could say, right, fraction bar, we could read it as a per if we wanted to. We could say there is a 9 degree what? Fahrenheit. Is it a positive or negative number? It's positive, so it's an increase. If it were negative, I would put decrease, right? There is a 9 degree Fahrenheit increase in temperature per what? Per 5 degrees Celsius increase in temperature. A lot of times we actually say the bottom number first because the bottom number represents what? The input. So in some instances, it would be really common to say a 5 degree Celsius increase in temp corresponds to or even causes a 9 degree Fahrenheit increase in temperature. So in the homework, when it says interpret the slope or write the slope with units, that's what you're being asked to do. So if we slide ahead to another example, I could just give you a random function, a model. This is a model. What is this one model? Speed of sound. It says the speed of sound as it travels through the air depends on the temperature of the air. And who can tell me why the speed of sound through air depends on its temperature? Do you know why? Don't let the math guy defeat the science majors. Come on, science majors. Why does speed of sound in air depend on air temperature? Depends on other things too, but one of the things it depends on is temperature. Why?
Because of the air molecules have more energy.
They do. When the higher the temperature, the more energy they have. What happens what happens when air molecules become energized like that? What happens to air volume?
It goes faster.
Volume or density. So you heat air, like if you set your balloon outside in the sun, what happens to the balloon? When the molecules get more energy, what happens?
It expands.
It expands. So the same thing's happening as you're heating the atmosphere. So as the molecules become energized, the atmosphere expands, and then you get fewer molecules per unit volume. So you decrease the density. So it's a density issue. As you change air temperature, you change air density, which then affects the way the sound waves propagate through the air. So this is a model that explains how that variation happens. So it says the speed of sound as it travels through air depends on this function, and V represents velocity of sound waves in meters per second at a temperature of C degrees Celsius. So when we look at this, we want to recognize that the inputs are degrees Celsius and the outputs are speeds in meters per second. And when I see the slope of this line, right, this has the y equals mx plus b form. I see that it's a linear function in a linear model in the sense that it's modeling something real. I know how this slope was calculated, right? The slope was calculated by taking the change in the output, that's the rise, and dividing it by the change in the inputs, which is the run, because the run goes along the input axis, right? So this has a Celsius axis and it has a velocity axis. Here's my rise, here's my run. So I know that it was calculated by doing a change in, what are my outputs? Meters per second. And my run was change in degrees Celsius. So when I look at this number right here, it has units on it. It's 3 over 5, but it isn't 3 because the numerator has to be the output units, which are meters per second, and the 5 has to be the input units, which are degrees Celsius. So even though this number doesn't have units, it does, right? They're just not written. And it makes sense if you think about it. If it didn't have units, this would be stupid. Because what is the output supposed to be? A speed. So if I think about this, this should be speed equals. So meters per second equals. What does it equal? It equals 3 over 5. But the 3 has units. What are the units on the 3? Meters per second. And what are the units on the 5? Degrees Celsius. And then we multiply them by something. What do we multiply them by? Times Celsius, times degrees Celsius, plus 331 is what? It's the vertical intercept, right? So it has units too. The 331 is the speed. It's an input of 0, output 331 meters per second. So if you're taking chemistry this semester, you've done a dimensional analysis or unit analysis. You know that degrees Celsius divided by degrees Celsius, those cancel, right? And what do they leave you with when they cancel? Speed. Speed plus speed equals what? Speed. If the units didn't cancel, the model wouldn't work. It would give you garbage. So what we're wanting you to recognize is that the slope of a line is always a rate of change, which is just another way of saying a speed. When you're working on a modeling problem, the slope of any line is a speed. And then I can interpret this, right? A 5-degree increase in air temperature causes what? a 3 meter per second increase in speed. As the density of the air decreases, the sound is able to travel through it faster. Does that make sense?
Yes.
So all of the problems where it says write the slope with units, this is what you're being asked to do. You're being asked to think about, hey, what's the slope and what are the units on the slope? And then what is that telling me? How do I interpret it? And what's causing what? Is the increase in speed causing the change in temperature? Does the sound moving faster cause the temperature to go up? No. The increase in temperature is actually causing the increase in speed. The input variable is causing the output variable to change. So if I revisit the first example, but I revisit it in a context that is showing up in homework 36, because that's what I was specifically asked to do. Same information on the first slide, but fed to you in a different way. This says an increase of 5 degrees Celsius yields a 9-degree increase in the temperature in Fahrenheit. So what you should recognize here is all I've done is taken and given you from the first slide. What have I given you?
Different input output.
And I didn't give a different input output. What did I give you? I'm putting arrows around it.
The slope.
You got fed the slope. And so the trick is going to, not even the trick, the skill, it's a skill, it's not a trick. There's no magical tricks in mathematics or science. It's a skill. The skill is to read something and recognize when you're being given the rate of change or the speed. And it isn't going to be given to you in an M equals kind of way in real life, right? Nobody in real life goes to work and their boss says, hey, M equals this. Can you do something with that? That's not how science works. You're working with things and you have to recognize when you have a rate or a speed. So when I look at what I've been fed here, an increase of 5 degrees Celsius yields a 9-degree increase in temperature, I need to recognize that this is a rate of change. I'm being told how one number changes relative to the other. Does that make sense? An increase, it's a change. Delta Celsius yields what? Increase. Delta Fahrenheit. I've just been given two changes. And a rate of change is a change in something divided by a change in something else. That's how we get speed. You know, how do you measure the speed of your car when you drive it?
Miles per hour.
Yep, it's a rate. It's a fraction. You're being told how distance changes per unit change in time. Delta miles divided by delta hours. It's a speed, it's a rate. It's the slope of a line. So you've got to recognize if I'm told how two increases or two decreases, or how an increase and a decrease, because decrease would just be a negative number. When I'm given two changes, I'm being given a speed. And I can write the speed two different ways. In this case, it would be legit to say a 5 degrees Celsius change causes a 9-degree Fahrenheit change, or 9-degree Fahrenheit. You can't always write it both ways legitimately, but in the case of temperature, you really can say it either way. So right now my head saw a rate of change and recognized that it could express it two different ways depending on what I'm asked to do. I could express this rate change, 9 degrees, 5 degrees Celsius. So my brain's recognizing I'm being given the information to construct a speed, and I can actually write the speed more than one way. And you can do the same thing with the car. If it's true that 50 miles corresponds to 1 hour, it's also true that 1 hour corresponds to a change of 50 miles. the relationship can be, with linear functions, usually legitimately written either way, depending on what you're being asked to do and what task it is that you're trying to accomplish. So there's the rate of change. Note that when it is 0 degrees Celsius, it is 32 degrees Fahrenheit. So I was just given another piece of information right there. What piece of information does that give me?
The B.
That's the B in the linear model. That's the vertical intercept. If it was a generic model, we would call it the what? The y-intercept. But I'm recognizing I have a vertical intercept, right? Because 0 degrees Celsius is corresponding to 32 degrees Fahrenheit. Ooh, anytime the input is 0, the output lands on the vertical axis. So from this perspective, if I write the information this way, if I write the ordered pair like this, which of these two do I want? Choice
The
A,
first one.
choice A or choice B?
A.
So let's write this over here again. The slope of a line is going to be the change in the output, because that's the rise. The outputs are on the vertical axis, so they correspond to the rise, divided by the change in the input, because inputs are plotted on the horizontal axis, so that's your run. So change in output divided by change in input. So if I write the ordered pair like this, what's my input?
0 degrees Celsius.
Yeah, Celsius is my input. So which ratio do I have to pick? I have to pick the one that has Celsius on the bottom. If I wrote my ordered pair input 32 degrees Fahrenheit, output 0 degrees Celsius, which is a legitimate way to think of it, but now I wouldn't have the B in the MX plus B model, then I would go with this because it's change in input on the bottom, change in output on the top. And the first thing is always the input, and the second thing is the output. And that makes sense, because do you get an output before you give input? The answer is no. Input precedes output by definition. So note that the relationship between Fahrenheit and Celsius is linear, and give a model for Fahrenheit as a function of Celsius. So the idea is I can get two rates and two ordered pairs from the information that's been given to me, but now I'm being asked very specifically to do something. Fahrenheit as a function of Celsius. F as a function of X, as a function of. The thing that comes second is the input. So you're being asked to, by being asked to do Fahrenheit as a function of Celsius, you're being asked to make Celsius the input. And if you're being asked to make Celsius the input, that means you're being asked to make Fahrenheit the output. It means you need this ratio right here, this rate here. This one you don't need. And then my model is Fahrenheit as a function of Celsius equals slope times input plus B, and B is 32 degrees. And there's my model. And that's your part A, right, for the homework, is extract the rate information and extract the vertical intercept information from the paragraph and put the model together. Is that okay?
Yes.
Yes.
So one of the other things that you're asked to do in that homework is to find and interpret the intercepts. Well, last week, what did we do for linear models? We found the intercepts. But last week, I couldn't ask you to interpret the intercepts because we weren't working with applications. So there was no interpretation to be made. Does that make sense? There was no interpretation. When I look at this, if I were just going to do a quick sketch on the graph, not as ugly as that, hopefully. The intercept's going to be up here. It has a positive slope, so it's going to be a line going like this. Does that make sense? Fahrenheit output, Celsius input. You know the ordered pair right here already. What's the ordered pair there?
0, 32.
0 and 32. And over here, you'd have to calculate this one. So there's more than one reason for finding and interpreting the intercepts. Sometimes the intercept tells you something about the domain and range. Sometimes the intercepts do not tell you anything about what the domain and range of the model should be. Sometimes one of the intercepts will tell you something about the domain and range of the model. So you want to know what the domain and range of a model is. So finding and interpreting the intercepts is a key part of determining model domain and range. It's also a couple critical points on the graph because either the input or the output corresponds to 0 at the intercept. So for that reason alone, it's worth interpreting them. So this intercept I already know. This one I would have to calculate, and to calculate this intercept, what would we need to do?
Wouldn't you solve for F, right? Fahrenheit?
I've already solved for Fahrenheit because my model gives Fahrenheit as a function of Celsius. So Fahrenheit's been solved for.
Oh, for Celsius then.
Celsius, I don't, it depends on what you mean by that. What do I know about the ordered pair right there? What do I know for sure?
The Y is 0.
There is no Y.
The F, sorry.
Fahrenheit is that there is no Y. And this is what I want to try to beat out of you guys. That's why the homework assignments on the front cover, what did they say in big bold letters?
Don't use X and Y.
Don't use X and Y because X and Y are stupid. They have nothing to do with this. Fahrenheit, Celsius, Fahrenheit. This is a model. I would only use X if it meant something like X-ray. Hey, the number of X-rays. Hey, I'll use X for X-ray because it makes sense, right? X and Y, we only use them when we have a generic setting and we don't have anything better to call them. But it wouldn't make sense to use Y for Fahrenheit, and it wouldn't make any sense to use X to represent Celsius. In fact, the problem that happens that I see, because after 21 years of doing this, is if students use X and Y when they get done and they have X equals, 70% of the time they have no clue what the X means. If they had just put a letter name that made sense, they would know what it meant. Hey, C equals, that's Celsius. So what we know is that the Fahrenheit is 0. So to find the intercept, we have to replace Fahrenheit in the model with 0. And then yes, have to solve for Celsius. So subtract Celsius from both sides. And then multiply both sides by the reciprocal of the coefficient. And what's that going to be? Negative 160 over 9. So in the homework, what it asks you to do is write the intercepts, including units, and then interpret it. Why do you think I ask you to write the intercepts including units? So 160 over 9, but what are the units on that?
Celsius.
Yeah, degrees Celsius. And then the 0 is actually 0 degrees Fahrenheit. And then this intercept isn't 032, it's 0 degrees Celsius, 32 degrees Fahrenheit. So interpreting it is just simply saying what the ordered pair is telling you. What is this ordered pair right here telling me? When it is 0 degrees Celsius, the temperature is 32 degrees Fahrenheit. When the temperature is negative 169 Celsius, the temperature is 0 degrees Fahrenheit. So interpreting is just that simple. It's just saying what the intercept is telling you. Is that okay? And the reason for putting the units on it is to help you say it right. Because what I've run into over the years is when students are just given an ordered pair, they interpret it, I don't know what to say. Well, it's because you're not thinking about the units. The numbers have units on them. This is a modeling problem. There's no X's, there's no Y's, there's Celsiuses, there's Fahrenheit. And then if you move down, the other thing that people usually struggle with is the contextual domain. So you're asked to do a contextual domain. So the thing that changes from last week, you guys would have put arrows on this thing like this, right? And then what would the domain of this line be based on last week?
Negative infinity to infinity.
Yeah, negative infinity to infinity. And then the range would be?
The same, negative infinity.
Yeah, the same thing. So, but the problem is it's a modeling problem. So can Celsius go to infinity? Can Fahrenheit go to infinity or negative infinity? Can temperature become infinitely large?
No.
No. So when the problem says find a contextual domain, what you're being asked to find is a domain and range that work for the model. It's clear that Fahrenheit and Celsius cannot become infinitely large. And so one of the things that you do is you look at the intercepts and you ask the question, do the intercepts put any boundaries on the temperatures? In other words, is 032? Can Fahrenheit get bigger than 32? Yes. Okay, so this intercept isn't going to put any sort of upper bound on it. It's okay for the arrow to keep going this way, even though we know it can't go forever. There has to be some place where it stops. The contextual domain is you finding where it stops, you finding where it begins. And then I come over here and say, hey, this is an input of negative 160 over 9 degrees Celsius. Is this the smallest Celsius temperature that exists? Is this the smallest Fahrenheit temperature that exists? And if the answer is no, then that intercept isn't helping me with the domain and range of the problem. Is that okay? So find the intercepts, interpret the intercepts, and then ask the question, do these put boundaries on the problem, yes or no? And if they don't, then you have to be more clever than that for the contextual domain. So for this problem, this is one where the science students should shine like bright stars. For the lowest temperature that you can get, what is it? What's the lowest possible temperature? Come on, science students. Lowest possible temperature.
273.15.
So what's it called? What's the name of it?
Kelvin.
Absolute zero.
Absolute zero. Absolute zero. So this one, there's no mathy piece on this, right? Let me keep this crud. If I were working on this, I'd say, hey, for my science classes, I know that absolute zero and my inputs are Celsius. So if I'm looking for my domain, I probably want to ask about it for Celsius. And then there, you're going to get, oh, 273.15. Or, hey, if you put this number into the function, so if you feed in negative, right, this is a negative number, minus negative 273.15, if you feed that number into this function as an input for the Celsius right there, then the Fahrenheit would output. And that would be the lowest possible temperature in Fahrenheit that you could get. So an interesting thing about absolute zero, see, here's some ask, is absolute zero possible? So what's it say about that?
Impossible to reach.
Impossible to reach. So you have a situation here where you know what the lowest possible temperature is. It's negative 273.15. That's probably good enough for government work. So you start going, okay, my contextual domain and range. So in this case, not a whole lot of math to do. You say my domain is going to be Celsius, not X. Celsius can start at, ooh, I have to decide, I'm gonna go 273 point, what was it, 15 with a negative. So I either need to do an open parentheses or I need to do a square. Which is it going to be?
Open.
Open, because they said that it's theoretically the lowest temperature, but what is it? Impossible. You can never quite get there. And then the range is going to be what is the Fahrenheits that go with it. So Fahrenheit is an element of, does anybody have the Fahrenheit temperature? Or do I have to look that back up? Be two ways to do it. Look it back up in Google, or what else could you do?
You can plug it into the equation.
Yeah, you could plug this, exactly. That's the point. You could plug this thing here that represents the extreme. You could plug it in here and just calculate F, the lowest possible Fahrenheit. We're way lazier than that. 459.67, 459.67, so probably was a 2/3 kind of a thing. 459. 459.67. And then, boy, you know, when I first thought about this problem, guess what? I knew that the lowest temperature was going to be absolute zero. So guess what question I asked myself after I looked up absolute zero?
What's the highest temperature?
Yeah, and then you're like, absolute zero. That makes you wonder, like, is there, you know, what's the absolute? Is there an absolute high temp? Is there an absolute highest temperature? And look, at Google's prompting me for it, which means I'm not the first person who was curious. And they're giving it to me in Kelvin, which would be normal in science, in Celsius. And there it is. There is, ooh, and what do they call it? Absolute hot. Highest temperature possible. There it is. So what is that? 1.42 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1.42 times 10 to the 12th. And that's what you would dump in on the other end. So this is an example of a problem. If you're doing it like on a homework, you actually would turn out to not calculate these as much as you would do some thinking. And the issue is the thinking's always going to be different, because there are probably infinitely many linear models that could be given to you if a person sat down to think about all of the linear relationships that exist. And then sometimes domain and range is something you calculate, but then sometimes it's just something you have to think deeply about. What are the extremes? What are the extreme cases? That the extreme cases will put constraints on the model, and that will become the contextual domain and range. The arrows I can't put arrows saying, yeah, go to infinity, because temperature doesn't go to infinity. So if we look at another example, are we okay with this one? I'm assuming that the domain, the range, the intercepts were more what people are bothered about. I don't know if that's an accurate assumption or not.
It is for me.
So I have two more simple models here that I made up today, and I made these up specifically because they give you different ways that the intercepts can show up, and then depending on how the intercept shows up, it may or may not give you useful information about the model. So here's a really stupid example. A salesperson makes a base rate of $500 per week and earns a $50 commission on each, and that should say item that they sell. So if you have something like this, you could do a linear function that talks about how much money they make. Hey, the money I make is, hey, I get $50 per item I sell. I'll use N for item, and big M for money. Plus I make $500 per week no matter what. So $50 actually does represent a rate because it's $50 per item. Change in money per change in items sold. There's a sense in which this is a naughty example because you probably can't sell partial items. So it's a little easier when you use time. So I could just as easily have said, hey, I make a $500 base wage and $50 an hour, which would be nice. And then I would have more of a true linear function, but this is a linear model and it works. So if you think about what the graph of this looks like, it's going to look just like the Celsius did, isn't it? It's going to go just like this, pop, pop, and the arrow's running. Maybe you can put arrows on there, maybe you can't. Find and interpret the intercept. Well, I know what this intercept is. It's 0 items, right? This is what you make if you don't sell anything. 0 items, $500. There's the intercept with units. Interpret it. If the salesperson doesn't sell anything, they will make $500. Does that make sense? Is anybody out there?
Yeah.
Or am I all alone? Does that make sense or not?
Yes.
Yeah. So 0 items, I still make the salesperson makes $500 a week, even if they suck that week. So then you go get this other intercept. Hey, you know what this intercept is? It's some number of items, and the output is $0. So we could take the time to calculate this. So $0 means replace money with $0. 0 equals 50 times N plus 500. So you get negative 500 over 50 equals N equals negative 10 equals N. So it's negative 10 items. So I can interpret this. This says if the salesperson sells negative 10 items, they'll make no money. And then what I should follow that statement up with is clearly that doesn't make any sense. So this part of the model is garbage. In fact, anything below 0 should be garbage. So this is a case where the intercept is giving me a bound. It's impossible to sell fewer than 0 items. So I shouldn't have any part of the graph over here. The worst I can do is 0. The graph has to start here and go up. So if I'm thinking domain and range, this intercept is putting a lower bound on things, isn't it? So domain, items is an element of the interval that starts at 0 and goes someplace. And the range is the money he makes, at least until he gets fired for selling no items, is going to start at $500 and go someplace. So that intercept was important to find and interpret and then identify that it actually puts a lower bound on the model. This one's a little bit more difficult because there's no way to mathematically put an upper constraint on it. What do we need to know an upper bound?
If he has a limit on.
Yeah, is there a limit on sales? Is he's sure in the hell not going to sell infinity items. He's probably not going to sell 1 million of them, right? There's some sort. So we would need to know more information in order to put a good upper bound on this. Does that make sense? And so I'd simply want to say something like that. Sometimes what you can do is, if you know what's being sold, you can do a little Googling and find out what was the best sales day ever. And then say, and you know, is that a perfect way of identifying an upper bound? No. But if there was a best day ever, it probably puts a good ballpark on what the upper number ought to be. Does that make sense?
Yes.
There was a rainbow trout problem, and for my solution for it, I went out and did some research, and I found for the river that the rainbow trout were taken out of, I went out and I did a little bit of research, and I found out what was the record rainbow trout for that river. And I said, this is probably a reasonable upper bound. It's unlikely that something bigger than this is going to happen for the typical person if they're just out fishing, right? So it's not a math issue on the domain and range. It's a little bit of a math issue in the sense that you need to find and interpret the intercepts to see if they put boundaries on things. But then it becomes more of a critical thinking issue. How am I going to put an upper bound on this? I know it can't go to infinity, so saying that it does is a stupid thing to say. How can I put something there that's reasonable? And a lot of times what is going to need to happen is you're going to need to make an assumption. And assumptions are okay in modeling and in the sciences as long as you tell people what your assumptions are. So I think a good constraint on this would be, if I knew what the item was that was being sold, I could do some research and find out, hey, maybe there was a max ever, and that might be something that's Googleable. And then I could say, I'm going to assume that the typical person will not sell more than the world record sales. And the world record sales was this, so I'm going to use it as the upper bound on my domain. And as long as you tell the reader, in incomplete sentences, as long as you tell the reader what your assumptions are, it's okay to make assumptions, but you have to say them or write them down so the person can read them. And that's not just the case in math, it's the case in science as well. We always have to make assumptions. When we do make an assumption, we need to say what the assumption is so that the reader can decide whether they agree with our assumption or not. As long as you make a fairly reasonable assumption, you're not wrong, even if it's a different assumption than what I make. So I can give you the solutions this week, which I will do like I always do, and you might see that I make an assumption on one of the problems, and you might even read my assumption and say, I don't really think that was the best assumption that could be made. And that would be okay. That's the whole point of saying what you're assuming, is to allow the reader to have a choice to disagree or agree with you, or have a discussion with you about whether or not it's the best choice. Are we okay on this one?
Yeah, so basically just make an assumption and just
Yeah,
back it
make
up.
an assumption, but make sure it's an educated, informed assumption. So put the research into it that you need to. Don't just pull something out of the rabbit's hat and say, here it is. Do a little bit of thinking and researching before you put something down. The next example is my stupidest example. But it's good in the sense that both intercepts make sense, and the intercepts clearly identify the domain and range. And in the homework, I know there are problems where the intercepts completely define the domain and range of the problem. So there's no research that needs to be done. The intercepts provide sensible boundaries for the domain and range. So on March 17th, at the start of the pandemic shutdown in Washington, Rebecca, how many days have we been shut down now? We have a running count on our calendar. Quick. What's the 132 days? Is that all together or just? That's all together. So 132 days we've been shut down now. So we keep track of it. So at the start of the pandemic, Uncle Bob had 1 million hairs. Due to COVID-induced anxiety, he's been losing 5,000 of them each day. This is a linear model smacking me in the face. So right here, this 1 million hairs, what's that correspond to?
At 0 days, there was 1 million hairs.
That's right. That's 0 days because it's at the start. So yeah, you're given the date, but the date is the start, and the start is always 0. So 0 days, 1 million hairs. So you could write it in words. You could write it 0 days. You could actually spell out the 1 million as a number. There's multiple ways you could legitimately do this model. These are 2 of them. I'm going to do 1 more. But I've been clearly given the vertical intercept, what's happening at the beginning. And then I've been losing them at 5,000 hairs per day. This is clearly a rate of change. Losing at 5,000 hairs per, there's the fraction, per each, per synonyms, per what? Per 1 day. That's a rate of change. And so I can right away construct a model from it. I could say, I'm going to use this ordered pair for fun. I'm not going to use this one. I'm going to use this one. Okay, if I do this hair equal to negative 5,000 times D, where D is the number of days since the start of the pandemic shutdown, plus how many I started with. There's a model. Does that make sense?
Yes.
You could give another legit model for this. You could say, if I'm losing 5,000 hairs per day, you could do fraction of your hair lost. Negative 5,000 hairs per, what'd you start with? 1 million. Threes kill each other. Now you know the fraction of your hair you're losing each day. It's still a rate of change. I'm losing my hair at this rate. And then you could say hair equals -1 over 200 times the number of days. And this is kind of nice because you know exactly when you're going to lose all of your hair, day 200. So we're like 130 some days in, I said. So he's got about 70 days to go. Plus, and here you would do 1 because this needs to be the amount of hair that you started with, but you started with all of your hair. 200 200ths of your hair is what you started with, so plus 1. They're both legit linear models that model the situation. Students usually wouldn't think to do it like this. I would think to do it like this because I like to keep the numbers Small. I think it's nicer to work with small numbers than large ones. But if it, let's say a student did it from this perspective, which would be common, does this model make sense to you?
Yes.
So this one, if you do it, it's got a negative slope, doesn't it? So it's going to go, if I just graph the line, it's going to go like this. But here you've got an intercept that is input day 0, output 1 million. Right? And you know that the model isn't, if you go this way, this is a days and this is number of hairs axis. So if you go to the left of the vertical axis, what's the issue with the days over here?
It passes 0.
Yeah, they're negative days. They don't make sense. So that part of the model would make no sense. He started losing hair when the thing started. So I can't draw this part of the graph. It doesn't make sense in the context of this problem. So I can see that I've got a domain and range being partially identified by this intercept. When I get to this intercept, it tells me something. What's the output? 0 hairs. So if you set 0 equal to your model, 0 equals negative 5,000 D plus, then you solve it for D, you're going to get D equals the negative 1 million over negative 5,000, but the negatives are going to cancel, and the zeros are going to die, the zeros are going to die, and what are you going to get? You're going to get the 200. So this is going to be 200 days. Zero hair, 0 hairs. So that's if I write it with units. So interpret it. In 200 days, he will be
Hairless.
hairless, bald. There's the interpretation of that intercept. In 200 days, he will be bald. If he goes bald, can he continue to lose 5,000 hairs a day?
No.
No,
No.
which means the model is done. It's terminated. So this one, I can only draw this piece of the line. And now I have, and this, so if I write this intercept with units, it's going to be 0 days, 1 million hairs. At the start of the pandemic, Bob had 1 million hairs. 200 days later, he was bald. There's the intercept interpretations. But those two intercepts are completely giving you the domain and range. The domain is the days get to run from day 0 to day 100. And the range is hairs are going to run from the smallest number has to go first. They have to be in ascending order. You guys keep putting them like running from your interval from 5 to negative infinity. Not your ascending order when you're doing intervals. So even though 0 paired with a million, I don't get to put the million first. I put the 0 hairs first. And then the 1 million hairs. There's my range. So those are really the 3 most common ways for the intercepts to play out. You either get 2 intercepts that are interpretable and they mean something, like with the Celsius model. Hey, when it's 0 Celsius, now I know the temperature in Fahrenheit. When it's 0 Fahrenheit, I know the temperature in Celsius. But those did not represent extremes. But I could still provide an interpretation. The second example, this intercept right here provided an extreme case, but the other intercept was actually absolute garbage and represented nothing in the context of the model. Does that make sense? Negative items sold means nothing. And then this one, where both intercepts were interpretable, made sense, but also provided the domain and range for the model. I didn't need to go to Google because the intercepts told me the domain and range. And those are really going to be, as you move through the homework assignments, you look at the practice exam, and when you get the exam, not this Friday, but the next one, those are going to be what you need to think about. And you know, what type of situation am I getting? Am I getting this situation? Am I getting this situation? Am I getting the Fahrenheit Celsius situation? There are three, those are the three most common ways for it to happen in a model. Which one am I being given, and what information are those intercepts telling me about the model, domain, and range? Once the domain and range is over, it's over. Like if we went back to this idea, but we change it from a commission. Let's say you change it from a commission per item to, let's just pretend they're making $50 an hour. So this would be, instead of 0 items, it would be 0 hours. Ooh, they didn't work that week. They still made some money. Life is good. I wish life worked like that. Can you come up with a high end on this now? Can you come up with a reasonable upper limit on the domain? So all we're doing is changing it from a $50 per item to $50 per hour. What would be a reasonable upper limit to put on that? And it's not a math question. This is just okay, I've got to think about what I know about the world I live in.
Maybe 40 hours per hour?
Yeah, 40 hours. And why would 40 hours make good sense as an assumption here? What happens at the 40-hour mark by law?
There is, they need to pay overtime?
They need to pay overtime. So not every business does, but if a business is following state law, bang, you would hit the 40-hour mark, and that model would be done, because you would probably be making time and a half. You would probably be making not 50, but $75 an hour, which would mean you'd have to do something called a piecewise function, where you say, hey, you're making 50 N plus 500, but only for the first 40 hours. And then this needs to be a different function here for overtime. And then some jobs jump to double time if you hit a certain hour mark. So the moment I change this from commission to hours, I suddenly have a reasonable upper bound that if I wrote down on paper as an assumption, most people would look at my assumption and say, well, it isn't always like that, because the world isn't black and white, but that was a reasonable assumption to make, and I can buy it for $1, right? My model works from 0 to 40 because of overtime law. Does everybody abide by overtime law? No. But do the majority of businesses abide by overtime laws? Yes. So domain and range, sometimes you get them through math, sometimes you get them through applying logic to the situation or doing some Google research. Anything else before we bug out of here?
No.
All right. I'm going to go ahead and stop sharing.
Thank you.
Uh-huh.